Okay. Hello, everyone who's here as well, here with us on site in Seattle. My name is Alex Plopski. I'm assistant professor at TU Graz, and I will be your chair for this session. Just to make sure nobody's in the wrong session, this is the session on post-tracking and localization. So we'll have 4 papers today. We'll have 2 papers being presented online. The first and the third paper, and we'll have 2 papers being presented on site. And the first paper is by Hongjia, Zhai, Huang, Qirui, Guanglin, Hujun, and Guofeng, Zhang, called NIS-SLAM, Neural Implicit Semantic RGB-D SLAM for 3D consistent scene understanding. And we'll first see the video, and then we'll have a chance to ask the authors some questions online.
I am Zhai from Zhang University. Today, I will introduce our work, NIS-SLAM, Neural Implicit Semantic RGB-D SLAM for 3D Consistent Scene Understanding. Previous implicit-based neural SLAM, like IMAP and NIS-SLAM, just only reconstruct the geometry and appearance information and do not model semantic information. Recently, some work pay attention to model semantic informations, like VMAP, NIDS, NIS-SLAM. But they use GT semantic, instance information to model it. However, GT information is often not available in real scenarios. Therefore, we wonder if we can recover the camera pose, scene and object level reconstruction, and consistent semantic field learning only from the RGB-D image sequence. An overview of our approach is shown in figure. Our system take RGB-D monocular data as input, and we use the pre-trained CNN semantic segmentation model to generate inconsistent noisy semantic results of multi-view images. Simultaneously, we can performance camera tracking and geometry and semantic reconstruction. Next, we will introduce our method from 3 parts. The first part is the hybrid implicit scene representation. We use high-frequency parametric encoding and low-frequency positional encoding to represent the scene. The second is the multi-view noisy semantic fusion strategy, which can lead to more consistent semantic observations. The last one is the loss function and optimization strategy. In order to better fit the geometric surface, we use a hybrid encoding of high-frequency tetrahedral encoding and low-frequency positional encoding as our scene representation method. The basic element of mesh is triangular primitive. Compared with cube, using tetrahedral encoding can better fit the surface. To model information at different scales, we concatenate multi-resolution features that obtained via barycentric interpolation. Our system consists of 3 decoders, geometry decoder, color decoder, and semantic decoder. The inputs of different decoders are shown in the figure. Next, we introduce the multi-view semantic fusion module, as shown in the black box in the figure below. The semantic segmentation network may produce inconsistent and noisy 2D prediction results for RGB images from different views. In order to learn a more consistent semantic field, we project the semantic prediction information of adjacent frames to the key frame, and obtain the fused multi-frame semantic observation information based on the corresponding confidence via softmax function. In this part, we show our loss functions. Reconstruction loss of color in depth, which perform pixel-by-pixel optimization between rendering results and ground truth images. The second is the SDF and free space loss, which can learn an accurate geometry filed by optimizing the signed distance function. To enforce spatial smooth of the parametric encoding, we apply the smooth constraints on features. Finally, we apply the semantic reconstruction loss to optimize the 3D semantic field based on single-frame and multi-frame semantic prediction. We apply 2 optimization strategies for our system. We use the segmentation confidence to guide pixel sampling, which can avoid areas with large errors during camera tracking. Besides, we use progressive optimization strategies to make loss convergence stable. The high-frequency information may lead to suboptimal results when the initial pose is far away from the ground truth. In the following, we show our experimental results from different aspects. We show the camera tracking result of ScanNet, Replica, and TUM RGB-D datasets. It can be seen that our method can achieve relatively stable and competitive results. On ScanNet dataset, our performance is only worse than Vox Fusion. On Replica dataset, only one scene achieves the second results, and rest scenes achieve best results. On TUM RGB-D dataset, 2 scenes achieve the best results. We show the tracking and reconstruction process from top views. The top and bottom parts show the scenes from ScanNet and Replica datasets. The red color shows the camera pose and trajectory estimated by our tracking process. The geometry and appearance of the scene are reconstructed by our mapping process. As shown in the figure, our method is able to reconstruct high-quality geometric surface and color texture information from monocular RGB-D sequences. We show the camera view rendering results of the reconstructed geometry. The 8 scenes are from the Replica dataset. As shown in the figure, our method is able to reconstruct a 3D consistent geometric surface. We show the camera view and top view rendering results of the reconstructed geometry. The selected scenes are from the ScanNet dataset. As shown in the figure, our method is able to reconstruct a 3D consistent geometric surface for challenging real-life scenarios. We show a portion of the reconstructed object surface. We rendering the reconstructed object mesh from different views. These objects are extracted from our segmentation decoder. As can be seen from the figure, we are able to model a 3D consistent semantic field, which can aid us to extract 3D semantic objects. We show scene-level and object-level reconstruction results on Replica dataset. As shown in the table, we achieve the best performance on completion and completion ratio for all scene for scene-level reconstruction. Only accuracy metric is worse than Point-SLAM. Due to Point-SLAM use TSDF fusion as the post-process, which will lead to better accuracy. For object-level reconstruction, our approach achieved the best results on all metrics. We show some visualization results of scene-level and object-level reconstruction results. From the figure, we can know that our approach can generate more high-fidelity surface and fill the whole of unobserved regions due to the smooth prior of our neural representation. We show the semantic segmentation result on Replica. From the figure, we can see that compared with the baseline, our method can better model a 3D consistent semantic information field. It can remove semantic noise information during reconstruction and inconsistency of different views. We show the results of neural rendering results of color, depth, and semantics. It can be seen from the video that we can reconstruct the geometry and appearance information of the scene very well. And at the same time, we can recover a 3D consistent semantic field from the noisy 2D semantic information. Compared with the baseline, our method can better model a 3D consistent semantic information field. It validates the effectiveness of our multi-view fusion approach. In this part, we show the augmented reality applications of our method. Augmented reality is one of the important applications of SLAM. We insert the ISMAR 2024 text logo and some AR objects into the replica scenes for rendering, which has better AR visualization results. We rendering the image and AR objects with our estimated camera pose. As shown in the figure, we can accurately represent the occlusion relationship between real and virtual contents via our accurate camera pose and rendered dense depth map. Thanks for watching.
So we will connect to the speakers in a second. Okay. Does anybody here already have a question that they would like to ask? Nobody in the audience, but anybody in online? I have not seen any questions being asked, and if not, then I will ask actually a question. the system right now seems to be very, very restricted in terms of space and can be used in a room environment. But how much, how scalable is it? How much do you think you can do the same, run your system and reconstruct a whole building, a whole environment? Or is it really designed for very, very limited spaces?
Oh, okay. Our system is based on for the indoor scenes. If you want to model the outdoor scene like or a building, you need to a more impressive nerve-based approaches to model the geometry. So the limitation, this is a limitation of our approach. We only work for small indoor scenes. Cannot extend our approach to outdoor scenes.
Okay, so as far as I understand, this is future work for you. Does anybody have a question now? We have one question here.
Hi, thank you. Nice work. May I ask what's the performance if the view is textureless?
The input of our system is RGB different. If you miss some texture, we can use the depth information to perform camera tracking. Also, in some extreme textureless regions, our performance may be not very real. Yes.
Okay. I don't see any more questions in the audience at this point. So thank you again, Hongjia Zhai, for your presentation. And we'll move on to the second talk of the session, Robust Collaborative Visual-Inertial SLAM for Mobile Augmented Reality by Xiaokun Pang, Huang, Zhang, Jinyu Li, Hujun Bao, and Guofeng Zhang.
Okay, everyone. I will present our journal work, Robust Collaborative Visual-Inertial SLAM for Mobile Augmented Reality. As AR applications become more popular, they are playing an increasingly important role. It relies heavily on spatial computing, where accurate localizations is vital. Modern solutions, as long as SLAM is capable of real-time tracking on devices like smartphones and headsets through multi-sensor fusion. Platforms like ARKit and ARCore have already delivered efficient and precise tracking, but they mainly focused on single user experience. From a technical perspective, multi-user AR relies on collaborative SLAM to ensure accurate localizations within a shared global coordinate. This requires not only robust collaborative mapping, but also seamless cross-map registrations and localizations. Additionally, scaling this system to support more devices introduced further challenges in terms of synchronization and resource management, as well as the scalability. In the field of robotics and computer visions, there have been extensive research on multi-agent SLAM. However, most of this research focuses on collaborative explorations and reconstructions with multiple sensors such as LiDAR and GPS. There are significant differences in terms of the resource overhead, map representation, and algorithm compared to the collaboration in AR, where devices are often constrained by limited computational resource. In this work, we proposed a centralized collaborative SLAM system with multiple devices to address the tracking challenges in multi-agent while also ensuring the scalability. Our contributions are as follows. First, proposed a robust multi-agent collaborative SLAM system for edge device. Second, introduced a lightweight and efficient online cross-agent map fusion strategy. Last, proposed a tightly coupled approach that synchronized the backend structure with the front end for accurate real-time post estimation. Here is the entire system. It is designed to be deployed across a flexible number of mobile devices or connected to a central server with Wi-Fi. On the front end, it processed image and IMU data to enable real-time post estimation with 6 degrees of freedom. The initial tracking information is then transmitted to the server, where the backend is responsible for consistency mapping. For the responsiveness and the robustness of cross-agent localization and registrations in collaboration system, we proposed an online map fusion scheme based on co-visibility error. We create a buffer of the latest keyframe from each agent, which allow us to access the locally observed map points. In this module, we perform descriptor-based 2D to 2D image matching between each newly arrived keyframes and those in the buffer. Using the results from this cross-agent matching, we applied the ransack algorithm for consistency verification. If the matching number exists a predefined threshold, we consider it to highly likely that the two agents are observing the same error. We then proceed to our 2D to 3D verification stage to localize the newly arrived agent within the global map. And we summarized the total optimization flow in our system. On the server side, we first utilized the post-graph optimizations to constrain the posts between keyframes involved the intra-loop and interloop. Then, subsequently, bundle adjustments performed to achieve the joint optimization of keyframes and map points across agents. The state of the local map in backend is then synchronized with the sliding window state estimation in local agent for completing the correction of the drift in the front end. The objective of sliding window optimization is composed of visual reprojection error, motion constraints from the IMU, and marginalization constraints. On the server side, we achieved a more accurate state estimation on the backend map through consistent observations from multiple agents and integrated into our sliding window. This integration aims to constrain the accumulated drift caused by local tracking in the front end. Compared to the traditional object function of VIO sliding window, we expand its constraint terms, treating the map point from the backend as an anchor to enhance the localization capability of the front end. In experiments, we validated that the localization accuracy on public VI dataset YORK and our own collected Wacom datasets, including the coupling of front-end sliding window localization and backend structure information, as well as collaborative localization on our multi-user AR datasets. Compared to the similar methods such as CoWINS and OpSLAM3, we demonstrated certain advantages. And then we utilized machine hole 1, 2, and 3 to perform collaborative mapping, similar to CoWINS, and we were able to achieve the cross-agent map registrations and fusion in multiple sequence inputs. However, our point cloud structure was more consistent than that of CoWINS, particularly in errors such as the wall. To validate the effectiveness of the online configurable error-based map fusion, we conduct a test in our collaborative scenarios involved two agents, machine hole 1 and 2. The two agents had a long-term real-time configurability field and consistent motion errors, which provide an ideal test environment for the proposed strategy. The result of the test shows that the online approach was able to sensitively achieve the cross-agent place recognitions, thereby timely completing map fusion. Next, we evaluated the system's performance with the number of agents increasing. The average time required for tracking in the front end is a stable range. Conversely, the time the time cost for backend keyframe registrations at a server show a linear increase. This trend is attributed to the server's necessity to start additional threads for requests from an increasing number of agents, consequently leading to a linear decline in overall system performance. Finally, we analyzed the network traffic on the agent side across 3 collaborative scenarios, as illustrated in the plot. The machine hold sequence involves 5 agents, while Wacom 1 and Wacom 2 each involves 3 agents. We observed that as the agents' movement become more vigorous in Wacom 1 and 2, they lead to transmit more data. In contrast, the agent's movement in machine hold sequence were relatively gentle, resulting in a similar amount of network traffic. We visualized the machine hold and the Wacom scenarios with each scenarios consist of 3 sequences. The camera pose from front-end trajectories and the point callout in backend are presented in different colors, enabling collaborative mapping in a multi-agent system. We visually demonstrate the impact of the proposed map fusion method. The map registration method based on back-and-forth model can easily miss the appropriate opportunity for cross-agent map registrations and fusion, resulting in the failures to align in global coordinate. Consequently, virtual objects can only be displayed in their own coordinate system from different perspectives. In contrast, the online map registrations and the fusion method based on co-visibility regions enable cross-map fusion through online image matching of co-visible scenes. And we deployed the front VIO on 3 iPhone 12 with a personal computer for collaborative mapping service and demonstrate a multi-user AR scene. We placed a virtual Ferrari on the table and observed it from the perspective of different users. We capture AR demonstration through screen recording and confirmed the smooth operation on mobile device from a third-person perspective. And all the demonstrations are present in real time. Thanks for watching.
Thank you very much. Are there any questions in the audience?
Hi, thank you. Network. So may I ask how you do the backend optimization for the overlap region? For instance, you have 2 sensors viewing the same region. So in the tightly coupling, do you just optimize each sensor and only do the registration between, or you do the tightly coupling for both sensors in the map points there?
Sorry, I'm quite I didn't get you.
So basically, what is the equation for your tightly coupling when you have overlap region for both sensors? So do you optimize both sensors rotation and translation in the overlap, or you optimize in each different sensors, only optimize the registration between these 2?
I still didn't get you. Sorry.
Okay, that's fine.
I'll try to paraphrase while I'm on the way. So as far as I understand, on the server, when you have multiple agents, do you optimize them together or do you optimize each one separately?
In backend, they are the only one global map, and they are optimized in the whole system.
But individually? Right?
No. Global.
So altogether?
Or.
Okay. I think this was the question, I hope.
Thank you. This is really nice work. Have you measured the resource consumption especially for the implementation on mobile phones?
What?
Have you measured the overhead of running your system on a mobile phone as compared to, let's say, AR Core?
Our baseline mirrored this, and it was about 45% of the CPU of our work, and ARKit was less, about 30% about.
Okay. My second question. So the demo that you showed, lovely demo, a perfect demo. It's similar to the question from before. This is a very SLAM-friendly environment that you're showing. It's very easy to work in those cases, right? What will happen if? How does it work in textureless environments?
What?
So can you go back to the slides with your demo? Is it possible? So this is an extremely SLAM-friendly environment. You have this image that's very easy to work with. What if your environment is textureless? How well does your system work then?
I still didn't get it.
So you know SLAM, Visual-Inertial SLAM needs features in the environment, right? So this is a very feature-rich space that you're showing. There's lots of features and lots of visual features.
Let me try to paraphrase. I hope I will paraphrase it correctly. How dependent is your system on good tracking of the mobile device? So if you have just a white background just a white wall,
okay,
and you cannot track very well, there are not many features. So
I think it's the drawback of feature-based SLAM system. So our system also will be failed at this case.
So the moment the tracking fails, your whole system will fail. Or do you relocalize as well?
Our module have this module for relocalizations.
Okay, so there's a module for relocalization. Any other questions? I don't see. Actually, going in the same direction. So for your relocalization, how well can you handle self-similarity? So if you have multiple areas of the same, that have the same appearance, let's say windows, can your system deal with that? Or is it more that you're purely depending on the SLAM to disambiguate this information?
I didn't get it.
Okay. Well, it was a bit complicated, complicatedly stated question. Do you have any questions anymore in the audience? No? Okay. Thank you very much. Okay. Our third talk will be again an online presentation. So we'll see a video first, and then we'll have the chance to ask the questions. The third talk is by Zhiming, Zheming, Daniel Haeufle, Schmitt, and Andreas, and the title is HOIMotion, Forecasting Human Motion During Human-Object Interactions Using Egocentric 3D Object Bounding Boxes.
Hello everyone, I am Zhiming. I'm here to present our work called HOIMotion, Forecasting Human Motion During Human-Object Interactions Using Egocentric 3D Object Bounding Boxes. The co-authors are Zhiming, Daniel Haeufle, Schmitt, and Andreas. We're from University of Stuttgart, Bionic Intelligence Tübingen Stuttgart, Heidelberg University, and University of Tübingen. Here is the outline of my presentation. I'm going to introduce the research background, related work, method, results, discussion, and conclusion. Well, human pose, it can usually be represented using the 3D positions of human body joints. Human motion forecasting refers to the problem of predicting human pose in the future from the pose in the past. Well, human motion forecasting can be applied to many XR applications, including human agent collaboration, redirected working in XR, low latency and precise interaction in XR, and safe and comfortable interaction in XR. Well, the motivation of our work is that we observe that while in daily human-object interaction activities, the human body movements are strongly influenced by the scene environment. For example, in this figure, the human is trying to pick up some objects on the table, and then his trajectory would be strongly influenced by the location of the table, and his detailed arm movements are influenced by the position of the specific objects. So we explore to use the scene object information to guide human motion forecasting. The main contributions of our work is that first we demonstrate the effectiveness of the egocentric 3D object bounding boxes for motion forecasting. We propose a novel GCM-based method to forecast human motions from body pose and egocentric object features. We conduct extensive experiments on 2 public datasets and report a user study to show the superiority of our method. Here we are going to introduce the related work. Human motion forecasting has been explored by many researchers in the area of computer vision and also robotics. People have used the recurrent neural network to do the motion forecasting by using the human pose in the past as input and then to forecast motion in the future. The multi-layer perceptions have also been applied to do the motion forecasting. And also the attention-based architecture have also been explored to do the motion forecasting. Well, recently, researchers have started to use a graph convolutional network by viewing the human body joints as a graph to do the motion forecasting. Well, traditional methods on human motion forecasting usually simply they predict the human pose in the future from the pose in the past. What we do is that we extract features from the scene objects, and then we predict future poses from the past pose and the scene object features. Well, here is the problem formulation of our work. We focus on the daily human-object interaction activities because in such kind of activities, the human motions are strongly influenced by the scene objects. We use the egocentric 3D object bounding boxes to do the motion forecasting because the object bounding boxes can be easily accessed in the XR environments. Our method is called HOIMotion, and it contains 3 main components, namely the post-object feature extraction, post-object fusion, and the motion forecasting. In the post-object feature extraction path, we extract features from the pose in the past, from the user's head orientations, and also from the dynamic and static objects. Well, the dynamic objects refer to the objects that the users can interact with, while the static objects are the background objects. We use a spatial-temporal graph convolutional network to extract features from the body pose. We use the MLP to extract features from head orientations and the scene objects. All the information are transformed using a discrete cosine transform, namely the DCT transform. Well, to do the post-object fusion, we treat the scene objects and the body joints as nodes in a graph. And then by doing so, we build a fully connected spatial temporal graph, and such kind of graph can be processed using a spatial temporal GCM to do the motion forecasting. Well, in the motion forecasting part, we use a spatial temporal GCM, which consists of a temporal GCM and a spatial GCM to extract the features. We use a residual GCM block to extract the features, and then use a decoder GCM to map the features back to the body poses. Well, we evaluate our method on 2 public datasets, namely the ADT dataset and the Morgage dataset. Both datasets contains the full body motion and the scene objects in various daily activities. We use the mean per joint position error as our metric. We use 10 frames in the past as input and 30 frames in the future as output. Here are the results on the ADT and Morgage datasets. The best results are marked in bold, and the second best are underlined. We can say that our method can achieve best performance at different time intervals at different data sets. We also observe that our method using only body pose as input, it can also achieve better performance than prior methods. This validates the overall benefits of our model architecture. Here are some visualization results. We can say that at different time prediction times, our predictions are more close to the ground truth than other methods. We also conducted an application study to evaluate the effectiveness of each component used in our method. For example, we remove the static object, the dynamic object, static and dynamic, the head orientation, and we find that while our method outperforms the ablated versions at different time intervals, this validates that each component used in our method contributes to the overall performance. Well, here are some visualization results of the application study. We can say that our predictions is more close to the ground truth than the ablated versions. This video shows some of the visualization results. We can say, well, at different activities, our predictions is more close to the ground truth than the predictions of other methods. We further conducted a user study to evaluate our performance. We used 20 samples randomly selected from the results and recruited 20 users to do the study. The participants are asked to rank different methods according to precision and realism. Here are the results from the user study. We can say that our method outperforms other methods in terms of both precision and realism. Here we discuss some limitations of our method. First, we find that our long-term motion forecasting performances are not as good as its short-term performances. This is a well-known problem in motion forecasting because with the increasing time of the predictions, it will be much more difficult to do the prediction. And our method is designed for the human-object interactions, and it may not work well for human-human interactions. Well, here we give some avenues for future work. First, we would like to explore other scene-object related information, such as object shape for motion forecasting. And we will also like to add some physical constraints for the predicted human poses to make our predictions more physically plausible. And finally, we would like to integrate our method into more motion-related applications, such as redirected working and the human-agent collaboration. Well, to conclude, the main contributions of our work are, first of all, we validate the effectiveness of egocentric 3D object bounding boxes for human motion forecasting. Second, we propose a novel method that consists of 3 components: the post-object feature extraction, post-object fusion, and the motion forecasting. Finally, we demonstrate the superiority of our method through experiments on 2 public datasets and a user study. The code is available at this link. Thank you for your listening, and here are the references used in the slides. I'm looking forward to your questions. Thank you.
Thank you very much. We will now be switching to Zoom, but Zhiming can already hear us. So if you have any questions, please.
Should I wait until we see her? So we're switching to Zoom, but how's it different than telephone?
Just on the screen. They are already
Beautiful. Thank you. I'm Henry Fuchs, University of North Carolina. I really enjoyed your talk. Can you say a little bit more about how this is egocentric? Is the video data sets from the egocentric standpoint of the head-mounted cameras?
You mean
How is it egocentric?
Egocentric. That is they actually in the data sets actually they contain the third view data of the human and of the objects. In our case, egocentric means when we use them, we know in the data set itself we have the humans and the objects in the whole environment. So it contains egocentric and no egocentric. For example, some objects are behind you that you cannot see. When we use the data set, we first filter out such kind of objects. We only use the objects that are in your field of view. We use that as our input because we observe that while in our XR environments, it's much more easier to get the egocentric information from the VR or from XR environment. So we filter out we selected the objects that are only in your egocentric view, and then we use that as our input to do the motion forecasting.
So, because we had, it was a bit difficult to hear. From what I understand, you take the whole scene and you predict the viewpoint of the user, and you're filtering out you're removing all the objects that are not within this field of view and use only the objects that remain as part of your forecasting. Is this correct?
Yes, and yes, and also because we have your view, because we have your head orientation, so we have your the view of the human, and then we only use the objects in this field of view, so that's egocentric view.
Okay, thank you very much. I see a question over there. I'll go to the back and then I'll come back to the front here.
So, hi, very interesting work and wonderful presentation. So this is Janendra from IIIT. A couple of questions. So first, following up on the previous question itself. So if I understand well, what you are doing is you are taking some frames of a particular scene where the objects are in the egocentric view of the user, and you're using that to estimate this thing, right? Is that correct?
Yeah.
Okay,
yeah,
perfect.
Yes.
So now in this case, the thing is over the time, the same objects may or may not be visible from the egocentric perspective of the human, right? As there could be occlusions towards the object from the egocentric view. So first thing, how are you handling these occlusions, or did you not encounter any occlusions in the data sets that you use? One, and second thing is, since you're already using MLP plus a combination of graph, GCNs, so there is a lot of computational complexity that I see. So while it may work well for the offline situations, but what do you think, or did you look at the computational complexity or the time estimate, in real time or what during the inference? So if you can answer that, thanks.
For your first question, yes, you're right. We use the egocentric objects, but actually we use this over time. For example, if if my head is in this orientation, and then those objects are in my view, so we use those objects to do the motion forecasting, because this is a very direct understanding, because only the objects in your view that has more influence on your behavior, on your motion. So every time we get the objects in your view, if you turn around your head, then your egocentric objects would change. Every time we always use the two objects that are most close to the center of your view, and then we observe that those objects would be more meaningful to your motion. And also, actually, we also have this application study in our experiments, and you can inspect. For your second question, sorry, it's too long, so can you shorten it a bit for your second question?
I will repeat the question for you. So what is can you do the inference in real time, and what is the...
Okay. Actually, we tested the time of our method one we find that is we find that the actually reported in our paper the inference time is good enough, and also it compares with prior methods were faster than prior methods, and also why we use the egocentric the 3D object bounding box, because the bounding box information is very simple, very easy to process. If we use for example, the 3D point clouds, that would be very difficult to do it real time. And also one of our starting point to use the egocentric object, the bounding box, is to make it fast, to be really useful for our XR environments.
But so you said it's fast enough. Do you have a metric? Can you tell us in milliseconds, for example, what is the inference time based on the scene complexity?
I think it's less than 100 milliseconds reported in our, I don't remember the amount, but it's less than 100 milliseconds to run the inference.
Was that 200?
Less than 100 milliseconds.
Less than 100 milliseconds for the inference. So we are running out of time, so we'll have one more question here, and I would like to ask everybody else to please go and ask your questions or give your comments to the authors on Discord so that they can answer the questions online.
Yeah, thank you. Thank you.
Hi, Eric Foxland from Amazon. Nice presentation. In your example, there were just two objects close together on a table. So I guess that the fact that you can see those in your field of view helps predict what you're going to do, because there's a high probability you're going to reach out and grab one of those objects. If there had been many objects, like a whole bunch of objects over a larger table, it would have less predictive value, I think. Did you test that and see whether there's diminishing value to including objects in the prediction?
Good question. Actually, we tested this. For example, what we do is that we selected from your view. We choose to the objects from that is most close to your view. For example, we choose 2 objects, 3, 4, 5. We find that using the 2 objects that are most close to your the view center is better than using more objects, because actually using more, usually for humans, we usually concentrate on the center objects. So we find that this would be more useful. Even if some objects they are not in your egocentric view, we added this in our method and find this would not improve the performance, and we have the application study in the paper.
Okay. Thank you very much again, everybody. Thank you again, Zhiming Hu, for all the answers. And if there are any more questions, please direct them online in the Discord. So we'll come to now to the last talk of this session. This will be again an in-person talk, and the paper is by Hanna Schieber, Xiyu Li, Niklas Corelli, Philipp Beckerle, Julian Kreimer, and Daniel Roth. And the title is ASDF, Assembly State Detection Utilizing Late Fusion by Integrating 60 Pose Estimation. We are switching right now the screens and resolving some microphone issues, so we can all get ready for this amazing talk. I think all the talks are amazing, so I'm not playing favorites. It seems we need 2 more minutes.
I'm sorry for the delay. We'll start any minute.
So Julian is ready. Okay, we'll go with this view. So Julian, you have the stage.
Yeah, thank you very much for the kind introduction, and sorry for the delay. There was a bit some tech issues here. Unfortunately, Hannah cannot be here today, so she's the main author of this work. I am the HCI lead of this project, and she did the main computer vision machine learning part in this. So she gave me a very good briefing, and I will do my very best to present it. And she is standby in Zoom, so if there might be any questions that I cannot answer, I might have to forward it to her and get her feedback. Okay, so first of all, I would like to introduce you to our research project. It is basically about providing augmented reality assembly guidance in the operation room. So here on the left, you can see that those surgical instruments can be sometimes very tricky and hard to handle because it's quite a lot. They are very different. And as a standard nowadays, there is still paper manuals. And sterile handling of paper manuals can be very tricky. And we try to overcome this limitation by augmented reality. Because any error in this specific situation endangers the patient safety and breaks the operation room workflow. So to provide sterile and efficient guidance, we aim to use augmented reality guidance. And in this context, we also enable an interactive and adaptive visualization. So on the right, you can see how this could look like. And such smart manuals can, for example, look like this. So we have some step-by-step assembly guidance, which makes the user guided through this assembly process. But this requires pose estimation and state detection so that we know where the individual parts are and what the assembly state is. At this position, I could also make a short advertisement for our demo upstairs, where you can try this live. So. So you can see that augmented reality is very useful in this context to guide the users through this complex assembly process by 3D visualization, but it does require 6D pose information, it does require assembly state detection, so we need a real-time markerless 6D pose estimation and assembly state detection, which is the main topic in this part of our research. So if we look at related work, we see that existing approaches tackle the individual approaches. So we have works that focused on the assembly state detection, that was focusing on the graph-based object tracking, introducing graph limitations and some other tricks on how to do this. But there is no overall concept which does bring all the features together and leverage the application of all those features in assembly guidance. So to put it in a nutshell, the existing deep learning-based multi-object approaches, they limit their objects and state detection to 2D tracking, they limit their evaluation to 1 or 2 objects only, or they only provide 6D object pose information without predicting the current assembly state, which is very important for assembly guidance. We address this limitation by providing 6D pose and assembly state detection. So ASDF utilizes the late fusion step to enhance the assembly state detection and 6D pose estimation. To evaluate our approach and boost further research in this area, we propose also an ASDF dataset which contains 3D printable objects, which allows for real-time testing and benchmarking with augmented reality assembly guidance. We evaluate our approach on 2 datasets, which is GBOT and ASDF, and compare it to several other methods of 6D pose estimation and tracking. So here you can see the overall layout. Our system combines a deep learning backbone and refinement steps for the assembly state and the 60 pose object pose, and fuses this together in a novel pose to state module. And this information can be finally fed to the augmented reality application, as you can see on the right, to guide the users through the assembly process. So let's first look at the backbone on the left here. So we extend YOLO V8 pose, which already incorporates RANSAC PNP for 60 pose estimation, by adding a classification for the assembly tasks. This is denoted as S in this figure and is also highlighted in green. As input for the deep learning, we use purely RGB data, but we also incorporate depth data, which is used to refine the translation output. The final assembly state detection combines 3 components, as you can see here, which is the deep learning-based state detection, the relative pose-based state detection, and the consideration of the previous state using a weighted late fusion. So if we look at this, we can see that there's a deep learning-based assembly state detection, which comes from the backbone and is used as an input for the pose-based assembly state detection. Each pose of an assembly part within a group contributes valuable information to the overall assembly state and vice versa. The currently assembly state informs the relative poses of the objects to each other. This knowledge is used as well in our pose-based assembly state detection. Our pose-based assembly state detection uses the relative pose between every object to determine the state. This information is known as we require this information anyway to generate the training data and the ground truth. So the translation refinement determines the movement along the z-axis, and we use it to have bounding boxes to determine the relevant surface points. We reduce these points to the ones closest to the camera plane, and based on these 2D points, we approximate the depth information using the depth input. This results in an approximated 3D points, and using this, we can refine the translation of the objects. So let's now look at the pose-to-state module, which you can see highlighted in our overall workflow. So given the inherent codependency between the pose and the state, we build upon the knowledge of this relationship in our pose-to-state module in a late fusion manner. This module is designed to forecast the state probability, SP, of the assembly state and the current point in time. Our pose-to-state module seamlessly integrates 2 key components, which is first the deep learning-based prediction, and second, the prediction derived from the pose-based assembly. By combining these predictions, our module effectively determines the final assembly state, leveraging both deep learning and the pose-based assembly state. So we weight the individual predictions of the neural network, the pose-based assembly state detection, and each calculator at the previous step in time. So here you can see an example data with the ground truth, YOLO V8 pose, and an ASDF with synthetic and real-world data. So the detected objects and the assembly states are also highlighted in this figure. And in the table below, you can see that we also evaluate the assembly detection performance and the 60 pose estimation on our dataset. So we can see that the rotation error is more or less similar between both approaches. Our translation refinement gradually improves the results, leading to a lower translation error compared to YOLO V8 pose combined with assembly classes. While this has an average translation error of 20.9, our module achieves a translation error of 6.70. In terms of assembly state detection, our approach further boosts the results compared to a pure class-based assembly state detection, and it can be also noted that that we improve the ADDS score using ASDF by over 10 points. Here we show a video. I hope this works. Comparing on the ASDF dataset, where we have ASDF on the right side and YOLO V8 pose combined with assembly classes on the left side. And as shown in the video, our poses are less flickering. So this is a bit more robust. For more details, given the time frame, I have to forward you to our paper and maybe questions afterwards. And in the next slide, in addition, we also evaluated on the GBOT data set and compared it also to GBOT tracking, which is in graph-based object tracking. And the data set does not provide assembly state ground truth data, so therefore we can only evaluate the 60 pose performance. And here you can see that the rotation error in degree and translation error in millimeter is given. And we can see that on the GBOT dataset, we outperform the neural network baseline. So that is without the integrated assembly state, which is GBOT with tracking, reinitialization, and the YOLO V8 pose. And we could also show that using ASDF, we can improve the 60 pose estimation performance based off assembly processes while using only 60 pose estimation instead of tracking and 60 pose estimation. And on this slide, I would like to quickly show you a video where you can clearly see how ASDF is able to outperform GBOT with the detected poses being highlighted. So we saw that ASDF outperforms or performs better than pure deep learning-based approaches on the ASDF and the GBOT datasets. However, for persistent AR visualization, robust handling of severe occlusions by hands or other parts must be also considered. So, for example, also reflective and transparent objects will be very challenging to track. And to address this, future work could integrate a multi-camera setup, which should further improve the overall performance and especially robustness in the real-world setup. So to conclude, we presented ASDF, which is a deep learning-based approach utilizing late fusion for assembly state detection and 60 state pose estimation. We evaluate the full pipeline from assembly state 0 until the full assembly, including errors into our test data sets to test their robustness. And we've seen that our approach and dataset represents a promising step towards developing comparable backends for robust and real-time augmented reality assembly guidance. So thank you very much for listening. I'm sorry for the technical delay. Please feel free to check out our demo upstairs and also our ASDF and website in our lab. I will try to answer your questions as good as possible, but I think Hannah is standby in Zoom to answer any more specific questions. Thank you.
Thank you very much. So can we switch this, back to the Zoom so we can see Hannah, who is also available for any questions you may have. And I would like to direct then the questions to the audience.
Hello, Dieter Schmalstrig from Stuttgart. How dependent or how well can your system handle view-dependent effects or view-dependent detection? Everything was laid out on the table in most of the examples. It could be that you can only tell one state from the other from one side, but not from the other side. How can you manage that?
I think I have to follow. Yeah, Hannah, go ahead.
So you mean if a different view angle would influence the result of the state detection?
Yes. For example, if the change of assembly state is only visible on the front but not on the back, or vice versa.
So, I mean, of course, it has to be visible by the camera, but it doesn't matter at which orientation the object is. So if the object would be flipped around and more unnatural and would have a more unnatural position, like not something you would do in a real scenario, but in our synthetic data set, we also have like every rotation of every object considering multiple views, multiple angles and stuff. I'm not 100% sure if I understood the question correctly, so I'm not sure if that answers it.
Let me try in a little more detail, because we've worked on a similar problem, right? There's assume you are in state N, and at some point you would like to, you could move on to state N+1 by adding something, or remain in the previous state, or say, I don't know. These are the three answers that the system can give. And is it able to tell from the learning, from what has been learned, whether this decision can be made or not?
It cannot tell this, no. This is not considered currently.
Okay. So I think it's an interesting direction. Thank you.
Yeah, thank you.
We have one more question here up front.
Thank you. This is really exciting work. I'm wondering, I have two questions about your future work. One is that reflective and transparent objects, that seems to be very important for the classes of applications that you're considering. So what are your thoughts on that? And my second question is, I like your multi-view camera idea. Do you have specifics on where that would fit in and what that would help with? Because it wouldn't help with transparent objects, I'm guessing. So what's your sense of how that fits into your story?
So maybe first answering the transparent part. So I mean, there are different options. There are some depth sensors that can also handle like transparent and reflective objects more well. So you could integrate depth data or depth prediction. I mean, for example, depth prediction would produce pixel perfect depth, but you would have the problem that the depth prediction also introduced some kind of error in terms of offset. So this is one thing that we considered in the past, but was not too successful. Then there are polarimetric filters which you could use, which basically break the light, and you would have 4 different kind of images which can be used. There are some works on pure 60 pose estimation for that one, but we have not tried it for the full assembly state detection yet, but it works definitely for single 60 pose object estimation. And what was the second question?
How do you see the multiple cameras coming into play? So where do you see the benefit of using them? Because, for example, with the transparent objects, it's not going to give you more information.
Yeah, exactly. So for the transparent object, this is not helping us. But if you can remember the one of the first images that Julian showed from the operating room, so the use case that we really address is relatively large. So in our testing scenario, we just had a few objects on a table, but the real setup is way larger and there are way more trays, so we would have to mount several cameras anyway. And some of them will have an overlapping field of view, some of them will not, and we also will have the camera from the augmented reality headset and where someone is every now and then moving around. So what that would give us is just another angle on some existing tools, so we could use it to refine the 60 object poses, for example. There's, for example, the work Cozy Pose. It's already a few years old. Also a single object 60 pose estimation, which uses basically multi-views to provide more robust approaches and also to align the cameras better. So this is something we are currently looking at, but yeah, so far no presentable results, I would say.
Thank you very much, Hannah. So, and also thank you, Julian, for the nice presentation again, and everybody else who has attended this session. We are unfortunately out of time. If you have any further questions, I would like to direct you once again to the Discord server, where you can ask Hannah and Zhiming and all the other speakers as well. If you would like to have more details, please enjoy your break, and maybe see you back here for the next part of the pose and the localization section.